In quantum mechanics, there are several big ideas that come together to explain certain phenomena. And then they're largely about differences between the classic way we look at things and this new alternative way we look at things. One of the biggest differences is that we are going to be treating waves and particles as essentially different ways of looking at the same thing. If you're looking at the classical approach of waves versus particles, classical approach basically meaning the way physics handled things until about 1900, 1905, 1910, somewhere around there, about 120 years ago. Classical approach states that waves and particles are two different things. Waves and particles, wave being like sound or light or ripples on the surface of a pond, particles being like throwing a rock. So waves and particles are different kinds of motion. And they can be largely distinguished by what sort of measurements you can take on them. There are some measurements you can take on both. For instance, if you have a particle, like you throw a baseball or something, versus if you have a wave, like you shout and the sound travels. What's the one measurement you can take on both a particle in motion and a wave in motion? Yeah, they both have a speed. That baseball, as it travels through space, has a speed. The wave, as it travels through space, also has a forward speed. So speed is a property that is shared by waves and particles. They're both something in motion, so they both have a speed. But what are some differences? What's something you could measure on a wave that doesn't make sense for a particle? Or what's something you can measure about a particle that doesn't really make sense for a wave?
I didn't hear what he said.
Amplitude.
Sorry, what was that?
Amplitude?
Yeah, a wave has an amplitude, and a particle doesn't really have amplitude in the same way. Waves have amplitude. What are some other things waves have that don't really make sense for a particle? Yeah, wavelength. And what else do waves have that you can measure? What's another important property? Yeah, the period or the frequency. Same idea, just different ways of looking at it. And also to some extent the phase shift and the vertical displacement, but those are really more about the way you're setting up your coordinate system. The wavelength and period and amplitude are really the important ones. On the other hand, what are some measurements that a particle has that a wave doesn't? Like if you got a baseball moving through space, what's something about it you could measure that wouldn't make sense for a wave?
Location.
It does have a location. A wave also kind of has a location. I mean, a wave could be spread out along lots of locations if you've got a continuing wave. But if you just got like a single pulse, that pulse does have a location as it travels. So location can be shared by both. Mass is a good one though. Mass is, a particle has mass. You can weigh how massive that baseball is. A wave does not have a mass. It's just the phenomenon of particles being displaced from equilibrium. But particle motion involves mass. And also, if you multiply mass times speed, what does that tell you? Momentum. And we're going to treat this difference in what you can measure as in classical mechanics, we treat this difference in what can be measured as one of the main things the main differences between a particle and a wave. If you can measure the wavelength, then it's a wave. On the other hand, if you can measure the momentum, then it's a particle. Particles have momentum and don't have wavelength. Waves have wavelength and don't have momentum. It wouldn't make sense to talk about the momentum of a sound wave. It wouldn't make sense to talk about the wavelength of a baseball. That's the classical approach. The quantum mechanics approach, the modern approach, and by modern, we basically mean after about 1905. 1905 being when Einstein published a very influential paper on this idea. Quantum approach is that waves and particles aren't really different things. Waves and particles are just different ways of looking at the same thing, or different aspects of motion. And specifically, if we're distinguishing waves and particles by waves have wavelength, particles have momentum, the quantum approach is to say that every moving phenomenon has a wavelength and a momentum. Every motion has wavelength and momentum. And specifically that the wavelength and momentum, for instance, that baseball has a momentum, also technically has a wavelength. The sound wave has a wavelength and also technically has a momentum. And the relationship between those is an equation called the de Broglie equation. And this is specifically saying that the wavelength and momentum are related by being inversely proportional to each other. That their product, the wavelength times the momentum, equals this constant called Planck's constant, which is ridiculously small. It's something like 10 to the negative 34th, I think. Yeah, about 6.63 times 10 to the negative 34, and the units are joules times seconds. So the idea is a sound wave, for instance, has a wavelength. Maybe the wavelength is a few meters or something. It also technically has a momentum. But if the wavelength is some reasonable size, maybe a few meters, and these have to multiply to this extremely small Planck's constant, what would a reasonably sized wavelength tell you about the effective momentum? If you've got a few meters times something equals this ridiculously small constant, what does that tell you about the momentum? If you've got a medium-sized number times something, and the result is very small, what does that tell you about the size of this number? Yeah, it's really small. So that means if, for instance, a sound wave has a reasonably sized wavelength, and maybe a few meters, it does technically have a momentum. It's just that its momentum is so ludicrously small that we wouldn't even notice it. Likewise, an object that has a momentum that's reasonable, like that thrown baseball, maybe has a momentum of, I don't know, maybe 30 or 40 kilogram meters per second. This is a reasonably sized number. So what does that tell you about the wavelength? Also really small, yeah. If the momentum is a reasonable everyday sort of size, then the wavelength is extremely small. specifically so small that it would be like maybe the size of an atom or smaller. So that thrown baseball definitely has a momentum that can be measured. You measure its mass, measure its velocity, you've got its momentum. Technically, according to the de Broglie equation, according to quantum mechanics, technically that baseball also has a wavelength. It's just that its wavelength is so ludicrously small that it's never going to make any difference. It's never going to be noticeable. Likewise, that sound wave has a wavelength that can be measured. Technically, according to the de Broglie equation, it also has a momentum. It's just that its momentum is so ludicrously small that it never makes a difference. So for most ordinary macroscopic situations, either a system has a measurable wavelength, but its momentum is so small that we can ignore it. So we call that a wave. Or it has a measurable momentum, but its wavelength is so small that we can ignore it. So we would call that a particle. So this divide, this non-overlapping categorization, waves and particles, mostly works. It's only when we're talking about something with a very small wavelength and a very small momentum that it can really have both. And this is where we get into things like light. Light has a very small wavelength, maybe a few hundred nanometers. So its momentum is sizable enough that it can't be ignored. Likewise, if you've got like a subatomic particle, a moving electron, its momentum is so tiny that we can't ignore its wavelength. So we have to treat it as a particle and a wave at the same time. How does kinetic energy relate to this? We can actually tie kinetic energy into momentum. We usually think of kinetic energy classically as a property of particles. But there's a very convenient way of tying together kinetic energy and momentum. And this actually goes back to how we define both of those quantities in the first place. Classically, what's our usual formula for momentum?
Mass times volume.
Right.
The velocity.
Mass times velocity, mass times, velocity, because it is technically a vector. We're going to assume we're just talking about treating it as a magnitude for now. So we're going to treat it as a scalar for the moment. So mass times speed. And what's our usual formula for kinetic energy? Yeah, 1/2 mv squared. So they're not the same thing, but they use the same inputs, the same variables, same measurements. So we can relate these to each other just by manipulating the equations. Specifically, what could we do to the momentum formula to make it look more like the kinetic energy formula? One way we could do this is by isolating V. Momentum over mass. And then substitute that in where we see V here. So we get mass over 2 times momentum over mass squared, which becomes momentum squared over mass squared. And when you simplify that, what happens? When we simplify, one of these masses is going to cancel out, right? So we're left with just momentum squared in the numerator and 2m in the denominator. So this is a very convenient way to relate the kinetic energy of a particle and the momentum of a particle. In fact, in quantum mechanics, we usually just treat this as the definition, a new definition of kinetic energy. We generally don't really mess around with speed at all. We ignore the idea of speed and we just treat momentum as the most fundamental idea of a particle. That this moving object has momentum, and its momentum can be used to find its kinetic energy as well, just by squaring the momentum, dividing by 2 times the mass. That way you don't need to mess around with speed as a separate quantity at all. You just treat the particle as a thing that has momentum, and then you can use this formula to calculate the particle's kinetic energy. You can even use this to find the kinetic energy of a wave, because a wave has a wavelength, therefore it has a momentum, So momentum is h over L, Planck's constant divided by the wavelength. And then you can substitute that in here and find the kinetic energy if you have an effective mass also. The problem with a photon is that it doesn't really have a mass in a meaningful way. So for photons, we use a different formula for energy. And this is one of the other big ideas of quantum mechanics. First of all, that waves and particles are basically the same idea, related by the de Broglie equation. Also, the redefinition of kinetic energy, that's not really a new idea. It's just a shift in how we're looking at what momentum is versus what kinetic energy is. But the big idea of light is that light, it comes in these discrete little bundles. Light is not just this continuous beam. That beam is made up of lots and lots and lots of tiny packets called photons. Discrete as opposed to continuous. Like for instance, if you're pouring water from a pitcher to a cup, macroscopically, it seems like that water is continuous. There's no individual pieces of water, it's just a continuous flow of water. But if you zoom in on that really, really, really small, you notice that the water is made up of individual particles called molecules. With light, it's kind of a similar thing. Light looks like a continuous beam, but it's actually made up of these tiny discrete particles called photons, these little packets of energy. And each one of those packets has a certain amount of energy. The energy of one photon ends up being proportional to the frequency. If a wave of light has high frequency, that translates to lots of energy per photon. If the wave of light has low frequency, that translates to just a little bit of energy per photon. And that doesn't necessarily correspond to the brightness of the light. The brightness of the light, the total energy transmitted per second, is really more about how many photons per second, as well as the energy per photon. But this energy of one photon is describing how the energy is split up into packets. Since it's proportional to frequency, we can write that as equal to something times the frequency. And it turns out that something, that constant of proportionality, is also Planck's constant. So this is generally how we would figure out how much, or how the energy of the beam of light is split up. It's split up into these individual packets called photons. Each photon has an amount of energy equal to Planck's constant times the frequency of the light. Any questions on that so far? Or alternatively, what else is frequency equal to? Think back to the very beginning of what we were doing with waves. Frequency can also be rewritten as what? If you think back to the idea of wavelength, because we've been basically defining waves as something that has a wavelength, how is frequency related to wavelength? Yeah, we can go back to speed over wavelength, because the speed is wavelength times frequency. That means frequency is speed over wavelength. So if we just replace frequency with speed over wavelength, we get h times speed over wavelength, Planck's constant times speed over wavelength. And since we're talking about light, speed is specifically speed of light, usually written as c. So we got the energy per photon is Planck's constant times the speed of light divided by the wavelength of the light. And wavelength is usually the number we're looking at when we're dealing with colors of light. A certain color of light might be 500 nanometers wavelength or 800 nanometers wavelength or something like that. So the wavelength is often what's known about the light. If you know the wavelength, you can just take hc, Planck's constant times speed of light, divided by the wavelength, and that tells you the energy of one photon. Again, this doesn't really have much to do with the total energy of the beam of light. That has more to do with how many photons are traveling per second. but this tells you how the energy is split up. Any questions on that so far? And H is the same 6.63 times 10 to the negative 34 joule seconds. But HC shows up so often, especially in this formula, that it's often treated as its own constant in its own right. And that has a standardized value that's probably worth memorizing. H times C is, and we usually write this not in joules, but in electron volts. And it's about 1,240, there. 1,240 electron volt nanometers. Nanometers is the unit of distance that's one billionth, I think, of a meter, 10 to the negative 9 meters. So this is an extremely short distance, but it's the usual unit of measurement used for measuring wavelengths. So those combine nicely. And electron volts is a unit of energy. One electron volt, the E here just means the charge of an electron. So the charge of an electron, or really the charge of a proton, because we're treating it as positive. And volt from 7b is just joules over coulombs. So if you look up charge of an electron or proton, the fundamental charge of an electron in coulombs and coulombs cancel out and you get joules. So that's how you would convert electron volts to joules. But often we would just leave it in units of electron volts anyway. Electron volt is a very small unit of energy, but it's a convenient unit of energy when we're talking about the atomic scale, very small stuff. So this is typically what we'd use for HC. Alternatively, you could use the usual 6.63 times 10 to the negative 34 joule seconds for H, and then C is the speed of light, which is about 300 million meters per second. Any questions on that so far? So that's two big ideas so far. First, that waves and particles are really the same thing, and wavelength and momentum are related by the de Broglie equation. Second big idea, light comes in these discrete packets called photons, and the energy of one photon is proportional to the frequency or inversely proportional to the wavelength. The third big idea is essentially an outgrowth of the idea that particles act as waves. And specifically, if you've got a particle confined to a limited region, a limited space, let's say you have an electron in a box. One-dimensional box, for simplicity. You've got an electron confined to a one-dimensional box. Classically, we treat the electron as a particle. We just treat this as like an extremely tiny ping pong ball that's just bouncing back and forth. But in the quantum approach, which turns out to be actually correct, actually modeling what's really going on, in the quantum approach, we got to treat it as both a particle and a wave. It has a momentum and a wavelength. And if we're treating this electron as a wave, what do you call it when you've got a wave that's confined to an enclosed region of space? If you just got a wave bouncing back and forth in a pipe, what does that create? Yeah, we get standing waves. The electron in this confined space turns out to act like a standing wave. And because it acts like a standing wave, there's only certain wavelengths that will work. You would have the n equals 1 case, the n equals 2 case, the n equals 3 case, the n equals 4 case. There's certain wavelengths that will work, and the in-between values do not work. They don't happen because they don't form standing waves. So only certain wavelengths work. And if you have a wavelength, you can convert that to a momentum. Other way around, wavelength converts to a momentum. So that means only certain momentums work. The electron can have this momentum or this momentum or this momentum or this momentum. The in-between values don't happen because they don't resolve to standing waves. And each momentum relates to a kinetic energy. So there's only certain kinetic energies that will work. The particle can have this much kinetic energy, or this much kinetic energy, or this much, or this much. And again, the in-between values do not happen because they don't resolve to standing waves. And this is one of the big results of quantum mechanics, that you can't have just any energy. You can only have certain specific values, and the in-between values do not work because they don't form standing waves. And so the way we describe this is energy is quantized. Quantized in the sense that it only occurs at these specific values and the in-between values don't work. In fact, this is really all quantum means. A quantum step just means a very small discrete step, but something that you can't go less than. You can go from this energy level to this energy level if you add exactly the right amount of energy. But you can't stop somewhere in between. The in-between values don't happen, again, because they don't resolve to standing waves. So this is one of the biggest ideas in quantum mechanics. As a result of all this stuff of particles acting like waves, if you've got a particle enclosed in a confined space, then it acts like a standing wave, which means it can only have certain specific values for wavelength, which means it can only have certain specific values for momentum, which means it can only have certain specific values of energy. Energy is quantized. It only occurs at these specific values and nowhere in between. Any questions on that so far? And different types of situations lead to different formulas for the energy of the system. For instance, this idea of an electron in a one-dimensional box is one type of system. There's a certain formula for the energy it has. One of the types of systems we're mostly going to be looking at, though, I think, is the idea of an atom. If you've got a nucleus and an electron in an orbital around it, the electron is in a confined space, is in a confined space in the vicinity of the nucleus. It can't go too far from the nucleus. It can't really leave the atom unless it gets so much energy that it breaks the bond. But if we take a look at an electron confined to an atom, that is going to act like a standing wave. And if we extend that idea to 3 dimensions, in 1 dimension, you get the standing wave shapes we've been looking at. In 2 dimensions, you get more complicated standing waves, basically the vibrations of a drum or ripples in a very complicated, choppy surface of water. In 3 dimensions, though, you get some very interesting specific shapes that you've seen before in chemistry class, probably, as electron orbitals. The reason electrons form these specific orbital shells, the sphere or the sort of double teardrop, the reason that the electron orbitals form these specific shapes is because those are the shapes that form standing waves in this 3-dimensional situation. And because they have to form standing waves, only certain values of energy will work. So this is the reason why electrons can only occur at certain energy levels. The in-between values don't work because they don't form standing waves in the atom. And the usual formula for that, if you've got and this is usually called a hydrogen-like atom. The usual formula is energy sub n, energy of the nth state, is negative 13.6 electron volts times z squared over n squared, where z is just the atomic number. So for hydrogen, it's 1, helium, it's 2, and so on, just the atomic number as seen on the periodic table. Negative 13.6 electron volts is just a constant in proportionality to make the units work out right. But the important thing is this divided by n squared. Because Z we're assuming is a constant. We're just taking one type of atom and sticking with it. But n in this situation can be any whole number. Again, this has to form into a standing wave. And it turns out that the standing waves have energy equal to this divided by 1 squared, this divided by 2 squared, this divided by 3 squared, and so on. So n can be any whole number. 1, 2, 3, and so on. And of course, it has to be positive. 0 doesn't work because you can't divide by 0. But any whole number will work. Because again, those are the ones that form standing waves. Also, when we say hydrogen-like atom, we're basically saying this formula works perfectly for hydrogen. If you plug in 1 for Z, this formula works perfectly. If you're trying some other atom that's not hydrogen, I think it has to be an ion with only 1 electron. So for instance, a helium ion with only 1 electron, or a lithium ion with only 1 electron. I think the idea is it works pretty well for small atoms that are ionically charged. They only have 1 electron. If you've got multiple electrons, that kind of throws things off. If you've got much larger atoms, that throws things off. But for small ions with only 1 electron, this works pretty well. So that tells us what values energy can have. The atom can have certain values of energy. The in-between values don't work. Any questions on that so far? And a very convenient way of mapping this out, a very useful sort of diagram, is to draw out the possible energies on we usually draw a vertical line. So if we just draw out a line, essentially we're making a graph with only one axis. We're just going to draw an energy axis, but no horizontal axis. A little bit of space there. So here's our energy axis. If we try plugging in some values for n, and let's assume we're talking about hydrogen. What's the atomic number of hydrogen on the periodic table? Yeah, just 1. So we're going to plug in 1 for Z, which means energy is just negative 13.6 electron volts times 1 divided by n squared. And again, electron volts is just a unit of energy, very small unit of energy. So we can plug in some values for n. For instance, if we just plug in 1 for n, we just get negative 13.6 divided by 1. So that's one of the possible amounts of energy that this atom can have, this hydrogen atom. And that should be the lowest possible energy. Because if we plug in more values, let's say we plug in 2. You plug in 2, you get 13.6 divided by 4, which is going to be 3.4, or negative 3.4. And note that because of the negative 3.4 is higher up than negative 13.6. Or if we try plugging in 3 for n, 13.6 divided by 3 squared, we get about negative 1.5. And so that's higher up than E2. If we start graphing these though, if we start plotting these on the energy axis, first of all, what's the biggest that this can get? If you just keep plugging in higher and higher values for n, if you theoretically take n out to ridiculously large numbers, what does this value approach? Yeah, if n gets larger and larger, this approaches 0. It never actually gets there, but it gets closer and closer. So I'm going to put 0 as the top of the chart here, because we know this can't get up to 0. It's going to get closer and closer, but it never gets there. And let me mark maybe just every 1. So I've just marked, each one of these tick marks represents one electron volt. So this is -2, -4, -6, -8, and so on down to -14. N is just any whole number. N basically is described as just which energy state it's in. And this is basically equivalent to the harmonics of a standing wave for a musical instrument. Like N equals 1 is for a stringed instrument, N equals 1 is the fundamental frequency, N equals 2 is the second harmonic, N equals 3 is the third harmonic, and so on. N is representing the same idea here. N is talking about which version of the standing wave we're looking at, or in this case, which electron orbital energy level we're talking about. But N equals 1 is the lowest possible energy state. In fact, if we mark that on the graph, E1 is -13.6 electron volts. That's going to be about here. And then E2, the next standing wave that can form, the next higher energy, -3.4. That's way up here. And then E3, the next one above that, -1.5. -1.5. It's about here. And we could keep going. We can plug in 4 for N. And note that we're not really saying anything about the state of the system right now. We're just charting out the possible values of energy. We try E4. We're just going to have -13.6 divided by 4 squared. So that's -0.85. That'll be about here. And what do you notice about these energy levels? As we increase N, what's happening to the gaps between energy levels?
They're getting smaller.
Right. We're getting smaller and smaller gaps. Going from state 1 to state 2, from the ground state, the lowest possible energy level, to the next excited state takes a large amount of energy. But if it's already in state N equals 2, it takes only this much energy to get up to N equals 3. And only this much energy to get to N equals 4. And then N equals 5 is going to be even closer. These are going to get closer and closer together as we approach 0. Because we've got to fit infinitely many bands into this space leading up to 0. But the first gap is going to be the largest. What this all boils down to is these are the only possible values. And of course, we could keep N going, getting closer and closer to 0. But the in-between values don't work because they don't resolve to standing waves. So if you've got an atom that's currently in the ground state and you want to raise its energy, all you can do is add exactly enough energy to get to N equals 2, or exactly enough energy to get to N equals 3. Because you can skip states. You can go from 1 directly to 3 if you're adding exactly the right amount of energy. So for example, let's say you wanted to go from N equals 1 to N equals 2. That's going to take a very specific amount of energy. And now that we've listed it, we can just subtract final minus initial. -3.4 minus -13.6 looks like plus 10.2. So in order to go from the ground state to the first excited state, N equals 2, you have to add 10.2 electron volts of energy. But how do you do that? How do you add energy to this atom?
Photon.
Right. The photon is the carrier of energy. If you have an atom at a certain energy level and you want to raise it to the next energy level, you do so by hitting it with the photon. In a sense, the photon is kind of acting like the heat plus work from conservation of energy way back in 7A. In 7A, we were saying that the delta energy total of the whole system was heat plus work. Now instead we're saying delta energy of the quantum system, in this case the atom, delta energy of the quantum system equals energy of the photon. And strictly speaking, we should say plus or minus, because it might be gaining energy from a photon hitting it and being absorbed, or the system might be losing energy by spitting out a photon with that much energy. But if you know the change in energy of the system, in this case the atom, you can set that equal to the energy of the photon that it absorbs or emits as an absolute value. We're going to say the energy of the photon that has to get absorbed has to be the same amount of energy as an absolute value. And what's our formula for energy of a photon? We've got a formula for that, right? Hc over lambda, energy of one photon. So you can set the energy of that one photon that gets absorbed equal to Hc over lambda. And we're going to be treating Hc as, I think that was 1,240 electron volt nanometers. So 1,240 electron volt nanometers divided by wavelength equals 10.2 electron volts. And now wavelength is the only unknown left. So how would you solve for wavelength here? Yeah, multiply by wavelength, divide by 10.2. So the wavelength is going to be 1240 divided by 10.2, which is about 122 electron volts cancel out. We're left with nanometers. So that would be the wavelength that the light would have to have in order for one photon to cause the atom to jump from ground state to first excited state. In other words, this tells you, what does wavelength tell you about light? How would you see the wavelength? Or what would you see that's different if the wavelength is different? Yeah, it's the color. So this means that a certain color of light has exactly the right energy per photon to cause the low energy hydrogen atom to jump up to the next state. Of course, 122 nanometers, I think, is outside the visible spectrum. It's too low wavelength to actually see. So this would be an invisible form of light, lower wavelength, higher frequency, and therefore higher energy. So it's outside the visible spectrum, but this specific type of light has exactly enough energy per photon so that when one photon hits the atom, the low energy atom, the ground state atom jumps up to the next state. If the photon has a different wavelength, if the light has a different wavelength, the photon wouldn't have the right amount of energy. So like 120 nanometers would have a different wavelength, therefore a different amount of energy per photon, and it wouldn't be the right amount to settle on exactly one of the permitted states, which means that photon wouldn't be absorbed. A photon with this wavelength gets absorbed, causes the atom to bump up to the next energy state, and a wave of light that doesn't have the right wavelength doesn't get absorbed. The photons just pass right through with no change. And of course, there's several that will work. You can calculate the wavelength to get from 1 to 2, to get from 1 to 3, to get from 1 to 4. All those types of wavelengths would get absorbed, but the in-between values just pass right through. And this ties into the idea of the absorption spectrum. If you've got cold hydrogen gas at the lowest energy state, that gas can absorb certain colors of light because the photons have exactly the right amount of energy to jump up to another permitted energy state. But other wavelengths don't work. They don't get absorbed, they just pass right through. And the collection of wavelengths that work, the collection that get absorbed, is called the absorption spectrum for that element. Any questions on that?
So is that where the Z comes in? to determine like the difference between the different atoms?
Yes, if you were using a different element, for instance, if you were using helium instead of hydrogen, you'd have a ×2² because helium is second element. So that basically just means all these values are going to get multiplied by 4 from the 2². Or if you're dealing with oxygen, that's Z=8. So everything would get multiplied by 8² or 64. All these values would be 64 times as big. But this is why different elements respond to different wavelengths of light, because they require different amounts of energy to jump up to the next level. And I'd recommend giving that a try on your own. Try how much energy does it take to get from 2 to 3 and figure out what wavelength is absorbed. Or how much energy do you have to lose to get from 3 down to 1, and calculate what wavelength of light is emitted as the atom loses energy in the form of spitting out a photon. And then try it again with a different atomic number and see what difference that makes. So experiment with different situations, see if you can figure out which situations result in wavelengths that are visible light, which I think is like between 300 and maybe 800 nanometers. You might want to look that up. But there are certain changes that correspond to visible light, which means as those hot atoms cool off, they emit light you would actually be able to see. Anything that's not in that range is going to be emitting light that you can't see. Infrared, ultraviolet, microwaves, X-rays, stuff like that. Any other questions on that? All right, feel free to email me if you have any other questions or any examples you'd like to try out later, and I will see you next time.